Welcome back, grade 10s. In today's lesson, we are going to continue learning about the atom. Let's look at the meaning of atomic number and atomic mass. Each element has a specific number of protons, and it is the number of protons which live in the nucleus that would differentiate one element from another element. So, for example, any element that has 3 protons in its nucleus, regardless of the number of neutrons and electrons that the atom holds, it will always be a lithium atom. Any element that has 26 protons in its nucleus, again, regardless of the number of neutrons and electrons associated with that atom, will be an iron atom. Now, in the periodic table, there's the number above the element, and that is known as the atomic number, which may also be represented by the letter Z. Now, this is a very important number because it represents the number of protons in the nucleus of that element. That means that it actually represents the identity of that element. You will also notice that the periodic table is arranged based on the atomic number of the elements, starting with hydrogen, which has an atomic number of 1. Going all the way to the right-hand side, there's helium with an atomic number of 2. Then we start on the second period, which starts with lithium with an atomic number of 3, and that continues to the right all the way to neon with an atomic number of 10. The next row starts with the element that has an atomic number of 11, etc. In the periodic table, the number below the element is called the atomic mass, which may also be represented by the letter A. What does the atomic mass represent? Well, as the name suggests, it represents the mass of the entire atom, but that is also equal to the total number of protons and neutrons that the atom possesses. Let's consider a hydrogen atom. A hydrogen atom on the periodic table has an atomic number of 1, and it has an atomic mass of 1. Now, this atomic number over here represents the number of protons. So, a hydrogen atom has 1 proton in its nucleus. Now, the mass of the entire hydrogen atom is 1 unit, and we know that proton has a mass of 1 unit. That's a relative atomic mass of a proton. So that means that the mass of the hydrogen comes from that 1 proton. That also means that there are no neutrons in this hydrogen atom. Now, let's consider a helium atom. A helium atom has an atomic number of 2, meaning that it has 2 protons in its nucleus, but it has an atomic mass of 4. Now, what we know is that because it contains 2 protons in its nucleus, and each proton has a mass of 1 unit, then this 4 has to include the mass of these 2 protons. Now, what makes up the rest of the 4? We learned that electrons are negligible in their mass, but that neutrons have a mass of 1 unit. So if the total mass of a helium atom is 4, and 2 of the 4 are made up of protons, then the balance has to be made up of neutrons. And so that tells us that a helium atom is made up of 2 protons and 2 neutrons. Let's consider a lithium atom. A lithium atom has an atomic number of 3 and an atomic mass of 7. This 3 accounts for 3 protons. Each proton has a mass of 1 unit, but the mass of the entire atom is 7. So again, we know that 3 of the 7 come from the 3 protons that a lithium atom definitely possesses. And so what makes up the rest of that 7? Well, that has to be accounted for by neutrons, and 7 minus 3 is 4, which indicates to us that there are 4 neutrons in a lithium atom. So in the nucleus of a lithium atom, there are 3 protons and 4 neutrons. What you need to take away from this discussion is that to figure out the number of neutrons inside the nucleus of an atom, we have to take the atomic mass and we subtract the atomic number. We also need to be familiar with the fact that the atomic mass has another name called the mass number. You may refer to either one, and you need to be familiar with both. So we may calculate the number of neutrons in an element as follows. The number of neutrons equals the mass number, also known as the atomic mass, minus the atomic number. It is the number below the element in the periodic table, which is A, minus the number above the element in the periodic table, which is Z. So let's practice by calculating how many neutrons exist in an atom of aluminium. The number of neutrons is the mass number minus the atomic number, which is 27 minus 13, which gives us an answer of 14. So that means that an aluminium atom has 13 protons and it has 14 neutrons. This brings us to the discussion on isotopes. As we already mentioned, atoms of the same element always have the same what. What defines an atom? What defines the identity of an atom? It is the number of protons that will define the identity of any given element. However, we do get elements of the same type, meaning that they have the same number of protons, but they have a different number of neutrons. So having a different number of neutrons changes the number below. It changes the mass number. So what does that mean for elements that have the same number of protons but a different number of neutrons? It means that they will differ in their atomic mass or in their mass number. And those are known as different isotopes of an element. Let's define an isotope. Isotopes are atoms of the same element, which means that they have the same number of protons, but they have a different number of neutrons. Isotopes are just like different versions of the same element. They behave almost identically, but isotopes that have more neutrons in their nucleus are slightly heavier. We need to understand that from the beginning of time, isotopes haven't changed and they won't change because the nucleus of an atom cannot change. It is a very, very dense and small space within the atom. All elements exist in nature as a mixture of isotopes, ranging from 2 different types of isotopes to up to 36 different types of isotopes for one element. So here we can see 3 different isotopes of hydrogen that are found in nature. Now, recall that these electrons over here, they do not contribute to the mass of an atom. A proton has a mass of 1 unit and a neutron has a mass of 1 unit. Now, all 3 of these isotopes represent hydrogen atoms. How do we know that? Well, that's because they each contain one proton. And the number of protons in the nucleus of an atom is what defines its identity. Protium has one proton. How many neutrons does it have? Well, it has no neutrons, so its atomic mass is 1 unit, and that is made up by the one proton. Deuterium has one proton, and it has one neutron. So therefore, its atomic mass is made up of the mass of a single proton and the mass of a single neutron, which adds up to 2 units. Tritium has one proton, but it has 2 neutrons, so it has an atomic mass of 3 units. So these are 3 different isotopes of hydrogen atoms. Let's consider the 3 isotopes of carbon. We have 3 isotopes of carbon, carbon-12, carbon-13, and carbon-14. All 3 of the above atoms represent carbon atoms because any carbon atom will contain 6 protons in its nucleus. Now, carbon-12, these numbers over here, the 12, 13, and 14, represent the atomic mass of the element. So carbon-12, well, it definitely has 6 protons, so therefore it must contain 6 neutrons, giving it an atomic mass of 12 units. Carbon-13 also has 6 protons, but its total mass is 13 units. So 13 minus 6 shows us that there are 7 neutrons in a carbon-13 atom. And carbon-14, which has an atomic mass of 14 units and 6 protons, will contain 8 neutrons in its nucleus. Hydrogen is the only element where its isotopes have unique names. Isotopes of other elements are named according to their atomic mass, like we saw with carbon-12, carbon-13, and carbon-14. So carbon-14 may also be represented as C-14, and this 14 represents the atomic mass or the mass number of that atom, which happens to be 14 units due to this 14. Now, how many neutrons would it contain? Again, this 14 tells us the mass of the entire atom. But we also know, based on the periodic table, that all carbon atoms contain 6 protons. Therefore, to work out the number of neutrons in a carbon-14 atom, we need to say 14 minus 6. So all carbon atoms contain 6 protons. Therefore, the number of neutrons in carbon-14 is 14 minus 6, which is 8 neutrons. How many neutrons does hydrogen-1 have? Well, the atomic mass is represented by this one over here. And we know that any hydrogen atom contains 1 proton. Therefore, hydrogen-1 has 0 neutrons. 1 minus 1 is 0. How many neutrons does lithium-7 have? Well, if we look at the periodic table, we can see that every lithium atom contains 3 protons. 7 minus 3 will give us the number of neutrons. So a lithium-7 atom has 4 neutrons. How many neutrons does aluminium-26 have? Again, we need to look for aluminium on the periodic table and find that its atomic number is 13. 26 minus 13 gives us 13 neutrons. Isotopes are represented by isotopic symbols. And when they are represented by isotopic symbols, we have the element over here, the symbol of the element. The A is the atomic mass or the mass number that goes above the atomic number. Both of these numbers are indicated to the left of the element symbol. I just like to remind you that on the periodic table, you have your element symbol, you have the Z, which is the atomic number above the element, and the A, which is the atomic mass or the mass number below the element. So note that isotopic symbols, the bigger number, which is the A, is represented above the smaller number. It's almost opposite to the way that it is represented in the periodic table. So how would carbon-12 be written? Well, remember that this 12 here represents the mass, the atomic mass of the atom. That is the A, and that is the number that will go on top. The Z is the atomic number, which, based on the number of protons, we can figure out from the periodic table for carbon is 6. So carbon-12 as isotopic symbols will be written like this. Carbon-14, similarly, the mass is the number that we display above, and the atomic number is the number that we display below. How would aluminium-26 be written? We have the 26, which is the mass of the atom above, and the number of protons, the atomic number, represented below. Now, symbols for isotopes are often just written as C12, C13, and Al26 without representing the Z or the atomic number below. And why is it that we can get away with doing that? Well, that's because for every particular element, the atomic number is always the same, and we can always derive that value from the periodic table. We can easily derive the 6 of the carbon or the 13 of the aluminium. In the periodic table, the atomic mass that's represented below the element is a number with decimal places rather than a whole number. Now, I know that the periodic table that you work with generally doesn't include any decimal places and only includes whole numbers. However, many periodic tables represent an atomic mass with decimal places, and that number with decimal places represents the atomic mass averages of all the isotopes of that element. So the way scientists go about doing that is they gather naturally occurring samples of an element and they identify the percentage occurrence of each type of isotope. Based on that, they work out a relative atomic mass for that element, considering all the different isotopes and also considering how often they each occur. So let's take a look at an example. In a sample of naturally occurring bromine, scientists found bromine 79 and bromine 81, with 50.686% occurrence of bromine 79 and 49.314% occurrence of bromine 81. Now we need to take into account both of these masses and how often they occur in our calculation in order to work out the relative atomic mass of all the different isotopes of bromine that exist. And in this sample, it's just based on these two isotopes and these two percentage occurrence. So the way we work it out is we want to work out what is 50.686% of bromine 79 and 43.314% of bromine 81. So very important. The percentage is a number divided by 100. That's what percentage means. So we have to represent it as 50.686 divided by 100. That is equal to 50.686%. And we have 50.686% of is always a multiplication in maths, bromine that has a mass of 79. Take into account that the number that we use here takes the entire atomic mass of the element. Over here, we're accounting for 49.314%, 49.314 divided by 100 of bromines with an atomic mass of 81. And so we can add up those numbers and we get a relative atomic mass of bromine of 79.99. This means that the relative atomic mass of bromine is 79.99 units, and this represents the relative average of all the different isotopes of bromine atoms present in nature, or at least present in this particular sample. So here are some important things that we need to note about this calculation. When you provide your final answer of AR, which is your relative atomic mass, leave out the unit of measurement. Make sure that you represent the percentage as the percentage value given as a number divided by 100, and make sure that you multiply this over here, this percentage, by the atomic mass of the element. If you're only given the number of neutrons of that element, you actually need to add the number of protons to get the full atomic mass of the element for the calculation. Let's try an example together. In a lab, 2 samples of iodine exist. One sample is the stable isotope of iodine. The other sample is the radioactive isotope of iodine, which is I-131. Stable iodine is absorbed and used by the thyroid gland in the neck to regulate metabolism, growth, and development. This is why we have to have iodine in our diet. And because people don't get enough iodine in their diet, in general, salt has been fortified with iodine to actually prevent thyroid problems in the population. Now, I-131 is used in the treatment of thyroid cancer because this isotope of iodine actually can be absorbed by the thyroid and only by the thyroid, and it is then able to kill the cancer cells. How many protons and neutrons does I-131 contain? Well, what we know is that the entire atomic mass of iodine 131 is 131 units. So we need to go to the periodic table, figure out how many protons an iodine atom will contain, and from there we can figure out the number of neutrons. Iodine has 53 protons, and that is based on the atomic number of iodine on the periodic table. And to figure out the number of neutrons, we would say 131 minus 53, and we'd get a value of 78 neutrons. The stable isotope of iodine has 74 neutrons. Represent this isotope using isotopic notation. Now, this question is a bit tricky because you're only given the number of neutrons. When we represent the isotopic notation, we need the atomic number at the bottom, and we need the full atomic mass on top. And to derive this atomic mass, we need to take the number of neutrons of this isotope, which is 74, and add the number of protons of any iodine atom, which is 53. 74 plus 53 will add up to 127. If the lab sample has 82.3% of the stable iodine isotope and 17.7% of the radioactive isotope, which is I-131, calculate the relative atomic mass of iodine in that sample? Well, we worked out that this 82.3% applies to I-127. So the way we would calculate it is 82.3% of the 127 isotope of iodine plus 17.7% of the 131 isotope of iodine. And when we add up these numbers, we get a relative atomic mass of 127.71. And that is the relative atomic mass of the two samples of iodine that occur at these rates in this particular question.